तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen how to design VLSI systems using Verilog, and we have considered both implementations on FPGA board as well as without it, and here is suggested number of applications for you to design on FPGA or ASIC. And so here is somehow around 60 or above applications are there, and some of which have already been done by other people, and both in industries as well as R&D institutions, and some of which we will touch in brief to start with, and then go to taking two design applications and consider little more elaborately the specification, the block diagram, etc., for you to make a start on your own application. And first one in the list here is what is called alarm annunciator, and as the name implies, we need to monitor different engineering parameters in industries. Especially it may be a power plant, it may be a cement plant, sugar plant, and so on, steel, anything that you can conceive of. In fact, even thermal, nuclear plant, whatever you want. So for all these, you would have seen probably on TV or in magazines or journals, huge control panels over which sit some flashing lamps, and that is precisely what is called alarm annunciator. And there are very many sequences in that, and over 80 sequences at least I have known. And this, if you are really interested, you can contact me for more specification on this, but I am not going to furnish any specification right in this lecture. And you can also go for automobiles and do some controller, intelligent controller meant for say anti-lock brakes. Say it's also called, I think, as ABS brake. It is basically, especially in foreign countries, this is in vogue, and this basically when you apply brake continuously, and if the road is slippery, naturally it will be a disastrous consequence if you jam on your brakes. So you will have to do what is called a pumping action you have to give on the brake, but you can't really control intelligently on the spur of the moment. So you need some controller which will do monitor the actual road condition, accordingly intelligently apply the brakes intermittently. For that you need a controller. You can design such a controller, and that's second one. And naturally for you can have camera, and which will focus all by itself. You just shoot any scene, it will automatically adjust its focal length. All these call for lots of intelligence being embedded in the chip that you are going to design. And what is shown here for different applications can are already in vogue as embedded systems, wherein normally 8051 controller, microprocessor controller, or even any other processor such as 8085 or 68000, or you can use what is called PIC, peripheral interface connect, and such devices basically they are controllers. You can design even that using either an FPGA or ASIC. And there are other applications such as automatic teller machines, which you are already familiar. And if you go to toll gate, so you may have to pay some octroi or other charges there. So such things can be designed by you. Automatic toll systems is what is mentioned here. And once again, coming back to the automobile, you have automatic transmission. See, you have to, this is only to dispense away with the application of the gear, which we do manually. So once you start your engine and then engage the gear system, and you forget about the gear thereafter, and until you come to your destination and stop the engine. Till then, you have to have once again an embedded system controller which will do this, this will dynamically change, because you may have to climb up the hill or go down the hill. There may be lots of ups and downs, pitfalls on the en route, and road may be slippery, and it may be raining or snowing or whatever. So all these conditions dynamically change. So accordingly, you will have to see what the conditions are, and then apply that which will make a safe transition from one gear to another. You can't dispense really with the gear change, it is there, but only thing is it is automatic. What all you have to do is just start your engine and then just engage gear at say D1 or D2 or D3, depending upon the place you are in. Normally at D1 is enough. Even I have seen personally that even big flyovers it climbs without with ease. And next is after automatic transmission, what you see is avionics systems. So airborne systems, there are many parameters to be measured. So all these you can implement, say latitude, altitude, and so on, and wind speed, all some of the examples. Then you have gone to airport. So you have seen lots of baggages going to and fro from one place to another, and source of baggage may be many, and likewise the destination may be many. And so you need to control all these conveyor belts basically, or it can be security system within, without opening the baggage, you have some X-ray taken on that your baggage, and contents reported. All this you can automate. And you know camcorders, which you use as a video camera, and it's basically analog domain, and you have a tape to record, and but this would demand again an ASIC design, and cell phone is a too well known thing. For communication, you normally use an analog, and digital is the processing, and you can design at least the digital part of this cell phone. And once you have cell phone, you need to have base stations from which it will be relayed to a next one, and so on. And that's how you get cell phone message. And you want to have a cordless phone, then you can have once again you may require some IC for that. And once again, coming to automobile, you can have a cruise control, and you can have you can just speed up to the limit that you want to go. Yes, this is especially useful if you are going on freeways, and that's highways in eastern countries you call. And once you lock onto a particular, you just accelerate to the desired speed, let us say 50 miles per hour, and then press a button which is the which will take over and maintain that speed, and you can release your foot from the accelerator and concentrate on just applying on the brake when the occasion demands. Otherwise, the cruise control will take care to keep your vehicle steady at 50 miles per hour. And next is curbside check-in systems. Say this is generally for parking. You want to park your car, and naturally you have to pay for it, and there will be automatic machines which will take in this and give issue a receipt for that. And so you can think of such application. And another is digital camera, which is very well known, and disk drives. Then you have electronic card readers. It can be for it's basically an identity card, and you have innumerable electronic instruments, for example voltage, current, etc., like a DMM that you use. You can have and once again all this would call for different chips to be designed, be it FPGA or ASIC, and you have electronic toys, games. There also lots of scope is there for you to develop such controllers. And next one is electrostatic precipitator controller. This we will take as one of the two for considering the detailed specification, and this is used in for ash disposal in thermal power plant. And next is encryption, decryption. You can think of hardware. This is mostly in vogue as software, and you can now the demand has come for the hardware encryption as well as decryption, and you can apply it to any part of the ATM machine or any such place where you want security. You want to send your data, your program code, etc. So all this call for encryption and decryption, and you can do so, and quite many researchers are already on the job, and quite a few VHDL implementations have also come. And then you have a fax machine, or you want to identify fingerprints, so you can have another system for that. Then if you want to have fire alarm system, especially multi-story building, huge complexes, you do require such systems where you want to detect the smoke or fire. So for these are all basically, if it is smoke, etc., normally americium nuclear material is being used, and basically it is to detect this smoke. And you can also detect fire by using a thermistor and so on. And there will be a central control where you report zone after zone, and if it is a huge complex, and within this zone there can be many such detectors, and every detector is identified and its location announced if there is a fire. In the event of fire or smoke, you can have an annunciation there. And for automobiles, you can think of global position system to pinpoint where the automobile is, or so that it directs the driver. A road map can be created on that. So there is plenty of scope for work here in global position system, and currently lots of research is going on this. And then home security system, you want theft control protection, or you want to have install gas leak, or you right in the kitchen. In United States I have seen quite many such places linked, and lots of sensors are put there to detect high temperature increase, or smoke or gas leak, and so on. And this will be normally connected through wireless to the nearest police station and or fire station. So we can think of designing such systems. And another application is for injection molding machine control, and normally you use for ABS plastic made components, such as plastic casing for your cell phone or any other equipment that you think of, or phone, for anything for that matter. So you can use for timing control, and that's what is called injection molding machine control. And then we have already seen a camera example. JPEG codec is also one such. If you want still picture, you need JPEG, and if it is a DCT based, which we have already seen, you need JPEG, and if it is DWT based, that's a discrete wavelet transform based, you need JPEG 2000. If you want motion picture to be processed in JPEG 2K like thing, you have a motion JPEG 2K for the same, and you can that's plenty of scope for you to develop algorithms, architecture, and finally implementation as FPGA or ASIC. Then life support systems, basically medical, one of the medical equipments which is listed down once again, and there are various ECG then and so on. I am not a medical person, so I can't derail much about it. And you have a lift controller, it is a very good candidate. FPGA can, I mean, or ASIC implementation can be very easily done for a lift controller. You can use for modems, and MPEG codec also you can use, some of which we have already touched earlier, and MPEG 1, MPEG 2 or MPEG 4, MPEG 7, all this can be implemented. And of course network cards many people have already done, and so is the case for network switches, routers, etc. You can also attempt some of this. And then if you want onboard navigation, whether it is air or ship, so you can use navigation purposes, whatever engineering parameters that is to be monitored, controlled, and you can use FPGA once again, and so also ASIC. So you know pagers, I do not have to explain all that, and so is the case for photocopiers. And for what is meant by point of sale systems is, you can you would have gone to shopping malls, super markets, and you have a point of sale system there. So all your bills are being routed there, and all your items that you purchase will be separately labeled and with a barcode. So they what you have to do is just expose, I mean, this barcode, and this point of sale system will accumulate all that and convert it into a bill, and then once you make your payment either through your credit card or ATM card, so finally a transaction takes place. And so for that you need a point of sale systems, and portable video games. So all that what you want, I mean, battery operated portable video games you can think of. And later on I think normal video games using the bigger displays will also be shown later on. And printer is too well known thing, and many people have done this. Peripheral interconnect is what I have mentioned already. This is basically a logic controller. So what is coming next is a programmable logic controller or a programmable controller. This is a higher end of PLC, and programmable controller can use, I mean, not only solve logic but also even acquire data in a limited way. And this is too well known for many of the industrial applications. And PIC is one such very limited thing, confined to say 32 IOs, etc., with one timer, etc. And normally that goes as an embedded system controller. And if you want have a quality control system, you can build a system which will do this. For example, you have an assembly of painted cars coming, and you can have a camera and then capture the video frame, and then compare it with a good known finish. So with this, whether it is pass or fail, you can record. All this can be done if you have a good control system, and for that, that's what we mean by quality control system. You can apply the same thing for any other industrial product. And robo controller is very well known. So it's basically using different motors, especially what is it called? What is the motor called here? So okay, I'll recollect later on and tell you what type it is. And then you can have satellite phones, and then scanners, then smart ovens you can have. Everywhere you need some lots of controls to be done, timing to be done. So is the case with dishwashers, and for all this you need control there. And the robo controller, I forgot, is the stepper motor normally used there. And you can have a smart scale, for example taking a weight, or when you purchase you can have a weight, and this can be linked with the point of sales terminal which we have already seen. And you can have speech recognizers, and then stereo systems. Of course it appears so simple an application, but these things are becoming more and more complicated these days. So it calls for lots of I mean it demands the need of a particular IC to be used. and teleconferencing system you can use, and for this you can have JPEG or motion JPEG or MPEG 1 codec, etc. you can use for teleconferencing. Then you can conceive of a temperature scanner or a controller for industrial purposes. That can be multi-channel, say 8 channel or 16 channel or even more, even hundreds of channels are there. You can design a controller which will take in JK thermocouples or thermistor thermocouple, or even simple temperature sensors like AD590 and the like. And you can have another system, say theft tracking system, and this especially is normally installed even in automobiles, cars, etc. So for that you can design such system. And then you can have TV set top boxes, especially when you are many cable people are offering this limited number of channels. You need to pay only what you want to see, the number of TV channels, and for that you need this. And of course you can have an universal PROM programmer, and you can design a PROM programmer for that, for not only PROM but also PALs and microcontrollers. All this can be programmed, and multiple of them, and lot many features can be introduced in this. And you can have, if you want, you can make a digital IC tester, and various ICs you can have, what is already covered or what is not covered, you can always add. And another application which normally is not touched by many people is the unmanned railway line crossing. You see so many accidents taking place because railway lines are unmanned. So I would rather suggest that one of you seriously take. I even have detailed specification, but I am not going to cover. You can try on this, and once again it is basically FPGA to start with, and then you can migrate to ASIC later on when it is frozen. And even VCRs, DVD players come with lots of ICs, and you can think of that as well. And although there are so many players around on that, and video game consoles, which we have already seen earlier, and this is an extension of a higher end version which you would have seen in many video parlors. And of course video phones you can use. We have already seen that JPEG or MPEG we have already covered. Along with the video conferencing, we can use do video phones as well. So you can think of this, and we will be clubbing JPEG as well as MPEG as well as this video phone video conferencing, and be covering little more in depth in terms of block diagram as well as the basic specification. So along with the electrostatic precipitator which we said earlier, and we can design washers and dryers. And the last one I have listed here, maybe around 61 or 62, I will leave it to you to count, is expandable Bethe thermograph, which I have myself handled quite a decades back, and I heard that it is still in vogue. And this is to sense temperature of the ocean without stopping the ship as such. And normally it is it uses a thermistor around 4.7 K at the tip of a spool, which will there will be a spool with twin bonded wire, and when it can be launched from the ship rear end, and when the probe touches the water, the recording commences. So you can have a strip chart recorder for continuous analog recording, or and digital output periodically sampled, and the depth it can cover is some 0 to 1500 feet, and as you go deeper and deeper, the temperature becomes colder and colder. And you can, by using this, you can find out what is embedded in the ocean bed, so whether mineral or oil. You can have and school of fish also can be caught by using this, and you can conceive of such application, and the list goes on and on. In short, it is limited only by your imagination, and we will go for two of the applications, and before that let us see, just recollect what we had to take care, what are the issues involved in digital VLSI system design, which you are already familiar. I will again remind you what is to be done. An efficient application involves designing with minimum of internal external hardware in addition to optimized codes. You had to not only optimize your Verilog code, but also reduce the minimum hardware, both internal in sense what is inside the FPGA that you have coded, or FPGA means, I mean, it also means ASIC. So, the design chip area is what I mean by internal here. External in sense you need to connect interface signals. So, no system will work without the interface. In fact, if you look at the cost considerations, it is the external hardware which takes more of the cost rather than the internal hardware, and this is true for most of the applications. So, you had to take care of both internal as well as external hardware while designing, and naturally it calls for a minimum of hardware because that is going to determine the your system cost, and this is in addition to the optimization of your codes, which we have already seen quite many times. And HDL code, so if it is Verilog or VHDL, must conform to RTL coding guidelines. This we have been repeatedly saying, without which no chip will normally work, and even if it works, it will give it will start malfunctioning, it will give all sorts of problems later on. And next point is system development can be dramatically expedited if based on bought out populated electronic cards. In fact, we have used the digital IO card as well as the FPGA card, which is a populated card, and populated and tested, so that you are relieved of the burden of developing this hardware, and that is the positive end of positive end. The negative side is that it may not suit your application. So, you may have to do make some amendments as we have done here, and by cutting and connecting elsewhere in the form of expansion IO ports and so on, and you need to add more push button switches, and in some cases you may have to add interfaces such as opto isolators, relays, etc. And we will have to take care of all this before you do. First you have to make an overall assessment before you take up the system development, and that is what we mean by going for populated electronic cards. At least for the when the quantity is less, this is a good idea to go for populated cards, and once it is proven, the hardware is proven, and you can tailor make for the particular application. Thereby you can make a cost effective system if it is going to be in large numbers. If it is not going to be in large numbers, you can rest content with the populated cards themselves. And this is an important thing. Next point, you have to use the right tools, must be used to minimize the development cycle time. So, we have already seen that simulation and synthesis as well as the place and route tools having been used. If you go out, I mean there are all the you should not just download institution tools and then be content. It will have lots of limitations, and you can't really make any worthwhile product that you want to sell in the market, or if you want to if you are aiming for R&D work also, you have to have the right tools, and in the proper mix you have to use in the right measure, and that expedites the development cycle time. So, let us consider two such applications. First application is the electrostatic precipitator controller, second one is the JPEG. This is H261, you can correct it as 263, I think the latest one is that one, and this is for video phone as well as for video conferencing, and MPEG codec, and JPEG and MPEG based on DCT we have already seen as a DCT-Q, and we need to add more modules to that in order to make the second application feasible. And what we are going to cover is only detailed specification along with a block diagram, but it is up to you to study and get see different sites or the references I have given towards the end of that, and if you still want more information, you can always contact me. So, let us go to the first application. This is called the electrostatic precipitator controller. It is used in fly ash disposal in thermal power plant. So, you see that when you go to a thermal power plant, you will be told that there will be several tons of ash generated every hour, and this is going to be a very cumbersome affair to dispose of. For example, if you release it in the air, the entire township will be covered by ash. This I have practically seen because I have myself handled one of these controllers. Of course, what I designed did not bring about that covering, but I have seen such a thing. Few units malfunctioning had covered the entire township, including suburban train, and which I used to travel. And so another problem is water stream cannot wash the ash away it will get clogged in a short time, no matter how big the opening is. And the remedy for this is as follows. It is to apply a very high voltage DC voltage of the order of 80 kilovolt in the EP is the electrostatic precipitator abbreviated, and if you do that, what will happen, the basic electrode is negatively charged and positive charge is on the entire chamber. So naturally the ash gets along with the flue gas is pumped in at a very high rate, and naturally it brushes past all this positive, because the whole chamber is along with the tubing that connects will be basically positively charged. So naturally ash gets this charge, and once it enters the chamber, it will see the electrodes crisscrossing the entire chamber. The chamber can be very huge and as big as a studio here, and it will be full of electrode, and that is negatively charged, and any ash which has already got positive charge would naturally get attracted to this electrode and gets deposited all over the electrodes. So in order to get rid of this ash, what we had to do is we had to activate special hammers, and so as to free the ash, and once you free it will fall down owing to gravity and collect at the bottom, and at the bottom there will be a stream of water going. Now like a tame bull or whatever you call, it will be washed away very conveniently. This is and each ash acquires the same negative charge, so I think it is one particle of ash will be repulsed, so it does not cling to each other, and these are all the without this application of 80 kilovolts, naturally the ash, the slightest of excuse, it gets airborne, and that is how it fills the entire township if left straight away. So the control panel is like this. So this is required because you have, when you design a system, what is apparent to the customer is the actual control panel, and what you see here is, and 4 digits display, one digit called DS1. This is to tell you different which mode we are in, and this is basically, it is not even hexadecimal. We will explain how what displays are there, and you have N1 through N8 displays for various parameters. Say for example, that's in order to generate 80 kilovolts, you need a very high high voltage transformer as well, and normally you would see that right on the thermal power plant, right on the top you may see, and most of the thermal plants have that right on the top, and that is abbreviated as TR, meaning thereby transformer, and if it is very high, this LED must be on. Similarly, if it is if it is high, it should be on. If it is very high, if otherwise a thyristor is there in order to generate DC supply from the AC supply, and we use thyristors for that, and for thyristors are also to be fired from this controller what we are going to design, and any thyristor overload, that is overload in sense basically it reflects as current there, and that also will have to be sensed and indicated here, and you have a transformer, therefore there will be some oil cooled, so you need a top float or bottom float, you have to know the oil position there, and this unit itself will work only up to a particular voltage. If the voltage goes below a particular thing, it has to indicate the under voltage. Normally it is minus 40%. If line voltage goes below, it will indicate here, and this we have already seen. Then here, as we mentioned that we apply very high voltage in order to collect the ash. So needless to say, depending upon the flue gas that goes past these electrodes at a rapid rate, along with the ash, will make the current, electrostatic precipitator current, highly fluctuating. So the voltage also will go up or down accordingly. So it always sees some valley and peak. So it goes up and down, and so also the current. So when that voltage peak has been arrived, that also will have to be indicated. That is what is here. This and you can put this controller in either a local mode or remote mode, that is indicated here, and the switch for doing that one is shown here, and 2 positions are there. And as we see that, I mean, since high voltage is involved, and the current at a particular moment may be quite high, and sparking may take place. It may be as bad as a lightning that you see up on the skies, and naturally that will lead to deterioration of the electrodes and eventual breakdown or burnout. So you had to count this sparking. Here we the term is sparks, and accumulator sparks will have to be displayed in an electromagnetic counter. So even if the power failure, this will have to preserve what all it has accumulated till date. And if you want to set the precipitator current, you can use the pot meter here, and this is the pot meter which we are going to see in the block diagram. And we have P0, P1 through P10 all a bone spot meter here. You can there will be a label here, and you can open that one and then set. Once set, normally you don't change till you want to make some other setting. And there will be two BCD switches here just underneath address that furnishes the decimal identification number for the controller. You can identify right from set from 0 through 99. That means 100 such controllers can be networked, and there can be one common computer system from which you can control or change the parameters of any of these controllers. And normal this intake for many of the thermal plants is quite high, because I remember that every 1 megawatt of power that you generate, you need 1 unit for this. And even if 1 or 2 units fail, normally they have units of 12 or some such thing. Even if one fails in that one, ash will get airborne. And you have a keyboard also here. It's not only a keyboard here that you see with this 4 plus 2 keys. This is to change the mode, up arrow as well as down arrow, and 3 other LEDs are there in order to measure the current, etc., voltage, etc. And then you have a timer which you can switch on, so that you can when you apply a HT, this HT is the 80 volts or whatever you want to apply. This is a toggle mode. If you press once, it will be switched on, and how rapidly it should climb up to the high voltage will have to be determined. And you can determine that by switching on a timer. If you want fast, you just repeatedly press this one. It will speed up, expedite the slope and so on. And you can go for what is called peak mode. So it's basically to measure the peak, etc. So these are all the controls that you need to understand in order to design. Now we'll go into the some of the function modes. For example, you can display minus there. If you do, it will indicate the precipitator current on the 3 digits that you have seen earlier. So here will be displayed the precipitator current. You use this display and use one of these keys in order to go from one mode to other. So minus mode takes the precipitator current. It displays the actual precipitator current. It is actually rated up to 1 amp maximum, and 80 kilovolt is the DC voltage, which is next. E stands for the precipitator voltage. And how many sparks have occurred per minute, that is also very important, because safety is very important. That can be got in H mode. And then how much maximum current that you can set is determined by 0 mode, so I maximum limit. And what is the normal standard current that you want to set? Normally you set for 75. These are all the set points for that. This is the maximum is 100, and the range is 0 to 104. This 104 corresponds to, so you know we are going to use an 8-bit ADC, and it's unsigned. So the 256 would correspond to 5 volts. 0 to 5 volts is 0 to all F's, 8 bits. So this 104 corresponds to that all F's. So that's what you had know, and so is the case for all other parameters. There are so many other parameters that you need to set initially. All this will happen, will have to be non-volatile. Therefore, it has pot meter has been used, which you have already seen in the previous setting P1 through P11 there, P10 there. And there are other parameters called slope control, then timer control, and so on. And you don't have to know about details of this. What all you have to know is 5 volts should correspond to 20. I mean not 5 volt actually. All F's 5 volt would correspond to 256 in decimal. 255 is the one which corresponds to this, or 100 or 104 in ADC output. And so is the case here. T control and slope after spark, and what is to be set is here, and the range that you need to cater to is here. So 0 would correspond to 0 of ADC output, binary 8 bit, and FF in hexadecimal of course, or 255 in decimal would correspond to 99 for this case, elsewhere 109 and so on. So is the case for this under voltage. UV is not ultraviolet, it is under voltage we have already seen. So that also you can set here. Normally 10 is set here, and up to 40 also is can be set. So then other parameters are the charge ratio, pulse current, loop gain, and this is normally for one of the, I think, precipitator current or the voltage, what is the gain to be set in the, because there are analog channels as well. And this is the address that I have mentioned already. This is the unit address, that this precipitator controller address, and base charge set, charging current, and peak value voltage. These are all the charging current, how fast it is charging, and what is the base charging current. These are all the parameters that you need, and all have the same notation. So 5 volts would correspond to 256 in decimal for 8 bit ADC output, and you need to find the peak as well as the value voltage. So it will alternately give the same display, 3-digit display that you have. Well, in blank mode it will give the peak as well as the voltage. And note that settings are there only for this, not for this, because these are all basic actual field measurement. So for example all this and so on, and that is what is given as set and range here. And this actually the rear end of the unit will have all this IO connections, and I do not have to go into the details because we have already covered different LEDs, etc. For example, alarm warning, all this are there in that, and this is thyristor overload, etc. Temperature high and precipitator current, all these are actual places where you want to connect. This is basically IO connection, so do not take very much seriously about that. And here comes the IO card. There are basically 2 cards, one is the IO 3 cards rather, IO card, as well as where the signal conditioning will have to be done, and it has electrostatic precipitator current. This is the analog op amp you have to use. You have to use in a differential mode 2-stage amplifier you can have. So and this first stage is for CMRR adjustment, so unity gain for that matter, and so is the case here, except that this will be sensing the actual current. You have a resistor here and then let the current flow here, this voltage flow here. For current you need to measure the voltage, and for voltage you need to measure the current. So there will not be any resistor, I mean there will be a resistor here for this, whereas there is no resistor here. So that is all the requirement here, and this goes as the I0 channel, and this goes as I1 channel as well as I14 channel. There is intermediate voltage also is required here, and we need a sample and hold circuit, and for that there is a control required, and this is 15 channel. I0 through I15 are different analog channels here, and you have to check supply as well, and you need a watchdog timer here, and a trigger will have to be created, and you need to know which is a positive cycle or negative cycle, that is what is here, and you need to connect the transformer here in order to know which cycle you are in. And here all the 7 circuits for opto isolated inputs. It is basically potentially free contact for various parameters that we need to measure, which we have already seen earlier as temperature high and so on. Some such 7 are there, and IO card also has some 4 relays at the output, and there are drivers. These ports are the ones which will have to connect it to the FPGA board, and power supply is what is shown here. This will go to field connection, and these are all the opto isolated output here. There are 2 such numbers here to inert, and there is a firing card here which will house a pulse transformer in order to give to the gate of the thyristor. There are 2 outputs such which will control a full wave thyristor, and for both positive cycle as well as negative cycle. And this is the FPGA that you will have to design, and AC positive negative we have seen. We had to have reset from watchdog timer, and sample and hold we had to create from the FPGA. Trigger also we had to create, and for ADC you need a start pulse, then output enable pulse, then AL also is required, so that you can give the address also from here which channel you are referring to. At one time you can do only measure only one channel input as such. This we have already seen, and I2 through I11 and I13 are for pot meters. So there is a clock output here, and which is also pumped in from the FPGA here, and you have 4 LEDs which you have already seen right in the panel, and you also need to have serial transmission. So RX TXD are required, and you need a spark sensor. This I0 channel is applied electrostatic potential control, and it goes to one of the ports here, and there are so many other ports such as listed here, and so many LEDs are also required for displaying different things. These are all basically output, and 2 BCD switches we have already seen, that also is required, and one bit output you required in order to apply pulse whenever a spark takes place, and this is the electromagnetic counter. That is also an LED to indicate when it is active, and a keyboard is also there. This you can connect to this in a matrix fashion or independently as a port, and then sense which key has been pressed. This keyboard is what we have already seen in the front panel. This is what is the FPGA card, and that is for the first application. Second application, you are already familiar with JPEG and MPEG as well as video phone, which is what is shown here. Image input is applied. DC to Q we have already seen in depth. What you have to design is the variable length coder as well as its inverse. This is at the encoder end, bit stream is output here, and which is received here at the decoder, and then inverse operation will have to be done, and IQ IDST also we have already seen how to do. Out comes the reconstructed image. This is the hardware reconstructed image which we have already shown to you as DCTQ previously. So around 30 dB you have got. It's a fairly good image that you have got, and so what all you have to do is you need to design the variable length decoder before you output the DCTQ output and onto the stream, and you also need to have a controller at the encoder end. Next is the decoder. It is just the inverse operation in order to get the reconstructed image, and the DCTQ is actually created in RAS scan order 1, 2, 3, 8, then 9 and so on and so on. This is per block. Per block is 8 by 8 pixels, and in VLC you have to code in this fashion: 1, 2, then 9, then go on to 17, then 10 and so on. It is diagonally it goes. It is called zigzag order, and right up to 64, and this is for the variable length code processing. The block diagram for the variable length coder is here. This is the main unit wherein DCTQ is fed, and each of the coefficients is translated into a variable bit. So at the lowest end it will be 2 bits, at highest end 28 bits. So finally all said and done you get a compressed bit stream here, and you need a FIFO so that you accumulate first all the bits and then finally transmit in a controlled manner. If you want, you can add one more called rate control, and there is a mux here so that you can get either the normal VLC or the header information. Header information is what you give, say, through the host bus as to what the picture size that you are going to send, and what is the bit rate. So all that information can be sent here, and that can be sent through the host, and reference for this application is given at the end, and there are papers as well to that effect from the speaker, and there is also a controller which handles all these activities, and when to send the header is indicated by this. Host will have to give this here, and when this is whole VLC is ready, will have to be given by the designer to say that header ready signal is setted, and host bus is what is connected here. So next is the we have a central controller for the VLC with send header ready clock, and from host you need to give the address as to where you want to send the header. Header is up to 128 bits, so several bytes is required. In fact 30 bytes are required, and that is the address. You need address for byte count, so that is what you give here, and a number of bits you have to send out through the bit stream also will have to be given by the host, and this is load is from the controller, which is to load the header register. These are all internal thing we should you should get from the RAM, which is stored, which was written by the host in the header RAM. Get 1 byte and load it here, and basically this left shift register you output that particular bit after bit as a stream here. That is how you can get the this is called header serial output converter, and next is the basic VLC generator. This also has a controller with so many DCTQ quantization which you get from the previous stage, and whether it is a DC quotient or AC quotient is being said from here, and a color component, which component you are processing is input here, then a write signal is there, of course there is a clock, and you have basically DCTQ applied here, and you have a subtractor here which will take the previous block DC value, and then that which is registered here in this registers, depending for 3 color components, 3 registers are there, and depending upon luminance or CBCR which can be input here through from the host, and which will identify which color component you are processing, and for each of the color component you have to process separately. So very first coefficient that you give is DC coefficient, and that is you have to take the previous value of the DC previous block and the present block, and subtract the two. Present is applied here, previous is applied here, take the difference, and then apply the DC VLC coder, which is nothing but a VLC table that is furnished in the reference that will be given here. And whether it is if it is AC coder, that also is governed by the same table, and once again you input here, and for this you have to find out from the table which code we have to pump in here, depending upon DC or AC there is a mux and there is a control there which will finally output at the bit stream here. And the reference, I hope it is clear. Are you clear? And you will get more clarity if you refer to the reference here, and these are all the standards references, right, for JPEG H261 and for MPEG 1, then MPEG 2, and this is a very good book on by K.R. Rao for techniques and standards for image processing. And next is from the speaker, there are 3 papers, one to the effect of DCTQ and another is for the VLC here. These are all IEEE conference at Florida and Geneva, and you can refer to these references, and there is also a journal paper in Elsevier to the tune of for MPEG 2 video encoder, and if you apply these 3 you can put together with the standards, you can easily code for the VLC as well as for VLD.
In the last 50 or so lectures, my colleague Dr. Ramachandran and me and I have given you a overview and a detailed design knowledge of digital VLSI system design. As introduced to you in the introductory lecture, in the first lecture, we went through the digital system design and advanced systems design, and more important than the systems being advanced, systematic design procedures, and how to use various tools available to convert the design into hardware description language, and from there to simulate it and synthesize it and place and route on FPGAs. Many examples were shown during the course of these lectures. Many demonstrations were made, codes were given, and you have been given a very long list of ideas on which you can work further to make your own designs. And you can very freely use any of the codes that was developed in the class, because they have been all tested and demonstrated. They are all working codes. So any of those codes you want, you can always use in your design for your system and make your design simple, your design effort simpler to that extent. Secondly, you do not have to limit yourself to the ideas given. These are only various ideas we had about what you can do yourself. Then many more things you can think of. The innovation, your creativity is the limit. You can go and do all those designs, come up with newer and newer designs. But the basic point is, whatever we have taught you are basics, and it comes with you along with this. You can improve your knowledge. As I said, it is technology independent, does not matter what technology it is. The designs are portable. You can also try it on other FPGAs, even though we have used Xilinx FPGA as an example in this course. So all these things you can do yourself and that way you can enjoy the whole thing, and I hope you will be able to, you were able to understand, follow most of these lectures, and whichever lectures you have not followed, go on repeatedly seeing them again and again. If you repeatedly see them, you will get to know the idea, and sometimes when you do not understand something, that is because you missed an earlier lecture or missed a concept in one of the earlier lectures. The idea is to go back to those lectures and see it again and again, then you will get good idea. But more importantly, it is not enough if you just see lectures, you have to try it yourself. Take simple examples, start writing codes, compile them, simulate them to start with. You do not even have to synthesize and place and route. Depends on the facilities available in your college or the workplace. But once you are confident with the simulation, then you go looking for hardware and then start your synthesis process, place and route, and try new ideas. You can submit project proposals either for competitions or for your own projects in the class, or in industry. If you are working in industry, you can use these ideas and then come up with solutions for the existing products that you are designing or new products. Your manager will appreciate all that. So we will be very happy, both of us would be extremely happy if you feel that these lectures have been useful to you in your quest of knowledge in the domain of digital VLSI system design. As I said digital earlier in one of my introductory lectures, is only digital is only one aspect of VLSI design. VLSI design has analog design. Analog is less than 10% of the total design, but it is effort wise it is non-trivial. You can try mixed signal design where both analog and digital will reside together in one single IC, single design. And then there are issues like CAD, computer aided design tools, fabrication issues, low power estimation, low power designs, and so many other things. Once you are interested in VLSI, there is so many areas you can pursue. So we would expect you to use these things properly, and we will be happy if you had derived the benefit that we had in mind for these lectures for you, and I hope you enjoyed listening to these lectures as much as we enjoyed teaching you this material. Thank you very much for patiently going through all these lectures. Goodbye.